Alex.
Do you need to use the PA system, or are you good instead of just speaking? I can echo. Okay.
You start this?
Yeah.
Oh, good. Hello. Hey guys, if you don't mind, you can take a seat. Hello. Oh. Hey guys, please take a seat. We can get started. So thanks again for coming to tonight's presentation. How many of you guys attended Big Data Day LA? How many of you guys attended Big Data Day LA? Just few. Okay. All right. How did you guys find it informative? Was it informative? Yes, that's good. So we have a great presentation tonight. Before we go on, I just have a few quick announcements. Next month we're going to do another Spark meetup talk. It's going to be on Kafka and Spark streaming. It's going to be at Playtica. I'll probably put up a notice sometime this week or next week. Before we get on to the speaker, I just want to introduce our host for today, which is Internet, and Jason is going to do a brief introduction. Please give a warm welcome to Jason.
Thank you. Thank you all for coming. A few logistics, as I think many of you are aware, there's no restroom here, so if you need to, we will escort you into the data center. Thank you for coming. Thank you to Subhash and the meetup group. Afterwards, if you want to see what this facility is all about, we're going to do data center tours after the discussion. Thank you all for coming, and if you need anything, just ask Josh or myself. So thank you. Appreciate it. There you go.
So with that, I just want to introduce Reynold. So Reynold is a co-founder of Databricks. He's also one of the initial persons who wrote the Spark SQL, and he's currently a committer on the Apache Spark program. He's also the current record holder of the Daytona GraySort 100 terabyte challenge. So give a warm welcome to Reynold of Databricks.
Thanks, Subhash. Can you guys hear me okay in the back? No? Is it better if I just speak like this? Yeah. All right. How do I turn this off? Okay, all right. This is the largest room I've ever spoken in. Even I had a keynote at the Spark Summit. It was like 2,000 to 3,000 people down there, and that room's probably half the size of this room. So tonight I'm just going to talk to you about a new effort. It's actually not that new anymore. It's been going on for almost half a year, and a lot of people are not using it, according to our last Spark Summit survey. Database. And before I start, can I get a show of hands? How many of you have done something with Spark. Prototyping, oh wow, a lot. How many of you use DataFrame already? Quite a bit. DataFrame. And how many of you have never heard of it? Yeah. How did you get to this event? So a little bit about myself. Subhash already introduced me, but I've been working on Spark for a long time, actually since pretty much the very beginning. When I was a PhD student in the UC Berkeley AMPLab. So that's where Spark was created. And we started, I and a bunch of other guys started this company called Databricks in San Francisco about 2 years ago. And when we started the company, we donated the project to the Apache Spark Foundation. So it's a better sort of governance entity for the open source project. As I was making the slide deck of this talk, I was going back to how we were talking about Spark back in 2013. And this is really, so before all this hype started happening with Spark. And the time we had a meetup and asked somebody if you heard of Spark, very few actually put up their hands. Very different from today. So back then, when we were pitching Spark, we basically emphasized two dimensions. One is performance, and the other one is usability. And for performance, actually, a lot of people initially came to Spark for the performance, because it was just how did this in sometimes like 100 times faster than Hadoop MapReduce. And at the time, big data, the de facto standard was essentially MapReduce. It's really painfully slow. And the other thing, which I think is probably even more important than performance, so performance is usually how when people, the reason people came to Spark, but after that it stayed mostly because of the usability compared with other data systems. And the reason is Spark actually provides a much higher level API to the end user, the programmers, which is substantially easier to use than a lot of other frameworks. And you can see actually nowadays, the world has changed a lot from 2013 to 2015. Almost nobody programs directly lower level like Hadoop MapReduce, big data API anymore. Even if you're using Hadoop MapReduce, you're probably using some other higher level API provided by Scouting, Cascading, or the other frameworks. And really, the world's sort of becoming easier to use. I think Spark started this effort. There's a lot of growth for Spark in the past couple of years. So we donated the project. It's actually kind of interesting. We donated the project to ASF, the Apache Software Foundation, at this point, mid-2013. And before that, there wasn't a Apache Spark. So it's kind of funny, people were searching for Apache Spark even before that. I think some guys in the community predicted we're going to donate the system to the ASF. Yeah, but you've seen, so basically Spark's enjoying hockey stick growth, but at the same time, there's another concept in particular the data science world called DataFrame that's really also taking off. And before I go into that, can I get a show of hands? How many of you consider yourself data scientists? Engineers, data engineers, most of you, right? And how many of you use single node data frames like R and Python? More than half. Cool. So for the rest of you, how do you really use data frames? Data frames essentially is very powerful data abstraction for single node such as Python and R. It's basically like a relational table with a lot of APIs on top of a relational table for data processing. So you can do your normal sort of selection, filtering, joining of different data sets and all that. So usually also a lot of mathematical and statistical functions that's available on the data frames. The other way is input output. So data frames you can typically read data frames from a variety of different files like CSV, JSON, Excel spreadsheets, and all that. So it's very popular among data scientists. It's basically, if you go on to like Coursera or Udacity to learn a data science class, this is usually what you learn in the first lecture and second. So Spark data frames was introduced, I think, back in March, released along with Spark 1.3. It's essentially a distributed data frame abstraction, so you can use Spark data frames to work with a larger amount of data than usually what the single node data frames can provide. It exposes actually an API very similar to the single node tools like Python and R. And as a result, it should be fairly easy. If you use a single node database, it should be fairly easy to actually learn Spark database. It should be the setting. And it's available actually in all the 4 programming languages Spark supports: Python, R, Java, and Scala. Now I figure the easiest way, and probably the best way to introduce DataFrames is probably to just go through some demos. And after this demo, you will be able to stalk every single Spark committer on Earth. For anybody, and figure out what their daily activity is like. So I'm going to be working with the open public data set that you can find, which is GitHub. So let's do this. How many of you use IPython notebook? Okay. So what I have here is this is actually what the commercial side of what Databricks does. We have essentially a cloud service that provides you Spark service, plus a lot of nice data science tools on top. And this is one of the interface for the application. Essentially, right now I have a Spark cluster launched in the cloud with a front end that's similar to IPython notebook attached to it. So, and how many of you know Python? For the rest that didn't put up your hand, what's your primary programming language? R? Java? Cool. Anybody use Scala? It's a couple. It's good that I chose Python instead. I think you can figure it out pretty much based on, even if you don't know Python. What I have here essentially is a notebook interface. You can view it as like the RStudio, presented in a slightly different way. You can type code in and you press Shift Enter, it gives you a result. Right? Fairly similar to even command line shell. So in the case of Spark DataFrames, there are different ways you can load DataFrames. You point it to, for example, a bunch of CSV files. You point it to maybe some Hive table. In this case, I've loaded a table. I preloaded a table into my own Hive meta store in this cluster. Go Spark commits for, and I can use the table function essentially to load it to create a data frame. So I'm just going to run this. And in Python, can you guys see this in the back? All right. So let's take a look at what the. So once I created a data frame, you can see. So this is essentially just a data frame, and the REPL string actually prints you the columns and all that. But it's not in a very readable format. You could actually do, for those of you that use pandas, you could use a lot of the pandas commands. For example, dtypes to actually print out the schema. You could also do a more powerful thing that's do columns, which just returns you the list of columns and all that. So this is a good way for you to understand metadata. For something that's like extremely large, what we found in the, I guess in the big data world is a lot of people actually work with logs and a lot of nested data. So actually a lot of what we do in the Spark data frame is also to improve the ability to support nested data. And one sort of caveat of that is, or one special thing is usually sometimes when you deal with nested data, you might get a lot of columns or very deep nested data structure. And for example, if you look at Twitter and you print the entire schema of a single tweet, the schema itself is actually much larger than the tweet. The tweet has 140 characters, but if you print the schema, it's actually pages and pages of schema. There's all kinds of information in single characters. So when you have very large schema, there's actually a print schema that would basically print the whole schema in a hierarchical format. So it tells you, for example, in this case, I have a commit hash. I have author name. So this data set is essentially what I downloaded from GitHub that tracks every single commit to Apache Spark, the project itself. And how many of you use Git? So in Git, every check-in you have, basically every commit is identified by a hash code that's unique, basically, hopefully across the lifetime of the universe. So this is what the commit hash is. And then it's the author of the who created the patch. And committer is essentially who actually committed the patch. So the committer can be different from the author. Usually the author is whoever actually created it, and the committer is the guy that decides to accept it. Sometimes they are the same, sometimes they're different. And there's all kinds of other stuff. You can also see this is actually one of the nested data structure. There's change files, which is just a list of files. Here. So let's just take a look at the content itself. Internet's kind of so this is basically the table. So you have, for example, the commit hash. I'm gonna skip explaining the parent hash. It's kind of complicated. The author. So for example, this commit is authored by Matej Zaharia, who actually initially created the project as his PhD dissertation. And this is Matej's email. If you want to email him, you can find this commit was made in 2013, June 4th, and it's created by Matej, this commit, but also committed by Matej. And this Matej's email again, and when it was committed. There's no encoding. This is like the subject of the commit, and this is the body of the commit. So basically, Matej committed something from somebody else's branch. It fixed a bug in the block manager timeout. And there's actually no file that was changed. The reason, for those of you that are curious, the reason there's no file to change is because this commit is a merge commit. As a result, it's actually, the commits that actually change the files are actually sort of the children of this commit. So now, once I have this data set, once I have this data set, I can do a lot of things, basically the usual filter, project, and all the things you want to do. One example is, for example, if we want to find out how many commits were made, basically in the last 12 months, we could just create a new data frame, and then create a new data frame for last year, and then just give it a filter. So we're using the committer date side of the filter, and then I want it to be greater than 2014 last year, basically a year ago, the same date. And then you can just run a count to see how many commits are there. So there's about 3,000 commits made to the Apache Spark project in the span of the last 12 months. So I'm actually lying a little bit. I took the snapshot of the data set about months ago. So this is actually only really the first 11 months of the last 12 months. Now, let's say if you're looking for people to hire, one of the good ways to actually find out who you can coach or top people to hire is actually by looking at open source projects and figure out who are the active contributors. That's actually fairly easy to do here. So it's actually very similar to what you would do in Pandas for our Python API. You just group by the data frame based on the author name, and then you just run a count, and then you sort by the count after to just display it. So, so you can see, Matej himself made actually 1,500 commits throughout the lifetime of the project. And the second guy is actually Patrick Wendell, who committed, actually, I need to do one more commit. Go to the second place. I'll do that today. And then I'm actually in the third place here. And it actually drops fairly drastically. For those of you that are actually curious why, the reason is, at some point, it's kind of a little bit interesting history about the project. I think about a year and a half ago, we switched from using GitHub's pull request merges to actually using a merge string that would squash all the individual commits in a patch. So if you had been contributing to Spark long enough, every one of your patches usually resulted in more than 5 commits in the past. And after a year and a half ago, we kind of switched and we squashed all the commits. And then, so basically the order of magnitude dropped almost by an order of magnitude for how frequent stuff gets committed. And as a result, if you start contributing now, it's much harder to catch up to people that are doing it before. Even though if I don't do anything. So that's like probably too much detail for those of you that don't understand the sort of nitty-gritty details of how Git works. But the other thing is, let's say I'm just interested in working on with recent commits, right? For example, Matei actually doesn't commit as much code anymore. He's more of a sort of visionary guy right now of the project. He cares more about the architecture and the sort of administration of the project, less so about the individual commits. So who are the most active committers last year? It's pretty easy to do too. Remember, just now we created last year DataFrame that basically only contains commit for the last 12 months. So let's just use that. Yes, this time I'm number 1. So last year I contributed basically like 200 patches. If you look at it, a lot of them is related to fixing documentation and test cases. And then you can basically see the whole, there's a whole new different group of people. Patrick's still pretty active, but there's a whole new group of contributors that are contributing. As a matter of fact, Spark is now the largest open source, or the most active open source project in the data space. There's actually over, I think, close to 800 people that have contributed to code by now. And a majority of them actually appear in the last 12 months. So now, if you're analyzing open source projects, one of the interesting things about open source projects, you probably a lot of people actually asked me in the past, is what components are the most popular among contributors? And one of the ways you can answer that question is actually just to look at the number of files. Number of times each file has been changed. So remember, this data frame is actually in a nested data structure. I had this array field that's basically each commit contains a list of files that changed. So if you come in here, if you expand this, you show, for example, this commit only changed one file, the basic operators, not Scala. So Spark's written in Scala, if you're curious. So how do we do that? How do we sort of count how many times each file, the frequency of changes to files, just on a nested field? So it's actually this function called explode. What explode does is it's actually just flattens the list. So you have some nested structure, for example, in this case, an array of files. Once you explode it, every one individual commit becomes multiple records in your exploded table. So for those of you that use Hive, it's very similar to Hive's lateral view explode. So you can just apply the explode function on the change files field, and then you get exploded to multiple records. So one file will appear in one record. And then you can just group by, I'm gonna alias, basically for the new column that's exploded, I would alias it to name the file, and then I just group by file and run a count again to see what files are changed the most. So here, as you can see, the build file, for those of you that know Scala, the SVP build file is actually changed 420 times throughout the life cycle of the project. And we introduced Maven build about probably 2 years ago, and the Maven build files change also very frequently. So if you look at what contributors are doing, a lot of them are really changing build files, updating dependencies, which actually pretty much matches my own understanding. And the third largest files are Spark context. Actually, Spark context probably get broken down into 2 files because at some point, before we donated the project to the Apache Software Foundation, this is the Spark context file. The package name is Spark, but once we donate it to the ASF, the package name becomes this, so it gets changed. So after it's changed, about 2 years ago, it's been updated 258 times. And this has been updated before that, it's been updated 216 times. So there's a lot of people that actually change the entry point of Spark, adding new functions, changing documentation. Often when you get sort of a new data set, a lot of the time what you would do is actually to understand the properties and attributes in the data set. And so there's largely a lot of statistics functions we built into the Spark DataFrame for you. So one example is finding frequent items. So finding frequent items in general is actually a fairly expensive way to do it. So you need to go over the data. Essentially, you need to build a lot of state in the data to run the giant NumPy. So it's actually we implemented a one-pass algorithm that's approximate frequent items. You can essentially just pass the list of columns you want to get the frequent items on, and the frequency of them appearing. So 0.1 means the item should appear at least 10% of the time. So in this case, I'm just checking the frequent, who are the most, which author appear the most, and which committer appear the most. Now, because it's approximate algorithm, you might actually get false positives. So you might get one of the guy that's in the frequent item list who's actually not that frequent. There's a chance it might happen, but the chance is very low. And given most of the time you're using this function to actually understand data, it's actually a pretty good way to process it. So it just creates me a data frame of 2 columns. And you can see these columns are not random, but just like a list of names that are appearing. So you can get essentially who are the more frequent contributors throughout the life cycle of the project. And I mean, right now, this data set is pretty small, so it's pretty fast to run even the exact version anyway. But on a much larger data set, you'd be a lot more efficient just running the one-pass approximate version. The other thing that's very commonly used by data scientists is this thing called a contingency table or cross tabulation. What it does is you give it 2 columns. It's trying to, it will tell you the frequency of the pairs that appear in the column. It'll be obvious once I join. So what I'm going to do, I'm just going to pick the commits from this year. So starting January 1st. And I'm going to find the crosstab of author and committer. What this table means is this is a list of authors that actually created the patch, and on the x-axis, it's the list of committers that actually committed the patch. So usually the guy that committed the patch, if it's not a committed, the guy that committed the patch usually is also the one that reviewed the patch itself, especially when the author is not the committer. And this is actually a good way to understand, for example, if there's a quick way to tell if there's any correlation between data. For example, is there any correlation between Reynold and somebody else? So you can see most of the stuff are pretty random, but I committed a lot of Sean Owen's tasks. But if you take a look, there's a 30 here. So Sean Owen authored 30 patches. They were committed by Sean Owen himself. So Sean Owen commits a lot of his own patches. This is actually pretty common because once you write the patch, if you're committed, you have the privilege to actually commit. So you don't need to wait for anybody else. You just need somebody to take a look to review and then commit. Yeah, so you can see. I also, so this is me again. I committed 15 of David's Liu's patch. David's actually a colleague of mine who worked very closely with me. So this actually makes a lot of sense. Let's keep going. It's a lot of zeros. I also committed a lot of from ZSX Rings, also another colleague of mine. It's actually pretty, Josh Rosen's another colleague of mine. So you can see, in general, well, I commit a lot of sort of my co-workers' patches because they're sitting right beside me or ping me and say, can you take a look at this? And, right. That's usually what I do. So now, given that data set, you could actually stock every Spark committer, or even just open source contributor, because the data set actually has a field on when the commit happened. So when that happened, unless somebody actually wrote a bot to do commits, usually it means the guy actually was sitting on the computer, typing the commands to commit a patch. So we could actually fairly easily just do that. For example, if you want to know my schedule, just filter the data frame on my name, and then just compute the hour. And then we're going to get a timetable. So what this does is the committer date is the timestamp for the commit. An hour just gets the hour, it turns it in as an integer. And the second hour, essentially, it's a shorthand for naming the thing as an hour. So it's actually a lot of the similar to SQL as well. And then we can do a group by and then just count. So you can see, let's do this. So you can see, I actually sleep. I don't do anything between 9 o'clock and 3 o'clock. It doesn't really make a lot of sense. So the y-axis, the value is commit count, and the ID field is essentially the hours in the day. So 0 means like minute. What's going on? Time zone, exactly. So it's probably based on. So I live in San Francisco, which is UTC +8, I think. So this is probably actually UTC. So let's fix that. It's just a simple way to fix it. I think you can convert it back to UTC by just +16, and then mod it by 24. And the reason to do the mod is so you don't overflow the 20. Right. Now it looks a lot more reasonable. I do not sleep during the day. So as you can tell, I'm fairly active after, I think my day usually starts around 9 o'clock. It's usually not by the way, I'm not taking into account the summertime here. We could write a much more complicated program to figure it out. Yeah, but here, I don't want to bore you with that. So as you can see, my day usually starts around like 9 o'clock. It's usually not the first thing I do to come to Spark. But often, sometimes when I wake up half an hour later, I might be looking some patches. And you can see a lot of a dip during lunch. So around like noon, sometimes I go to lunch. And as a result, I don't want to commit anything during that time. And my productivity actually peaked in the afternoon, actually around 4 o'clock. That's when nobody's bugging me anymore. And then sometimes I have lunch between 6, 7, 8. That's why there's another dip. And then you can actually see me peaking again at night, somewhere around 10 o'clock. But usually nighttime is actually the most productive time now. Nobody can email me. I can ignore emails. And then usually I go to bed around 1 o'clock. This actually matches it pretty well. Just with this script, you could start it. I mean, you can look up the schedule of anybody, pretty much. Or you could, if you point it to a different repository, you can look up any other guys. Okay, so now we can answer this question. Let's move on. One thing I didn't talk about is a variety of input outputs that Spark DataFrame supports. So the only thing I show you is really this table that reads from a Hive table. It's actually a unified interface to read a variety of different data sources. So the interface starts, so SQL context is actually the central entry point to the DataFrame thing. Table is actually just a method on the SQL context. I pre-imported the function, so I didn't just type SQL context. But in reality, it's actually SQL context on table. Now, there's actually a reader that you can use. Once you call the read function, there's a bunch of different things you can specify. For example, you can specify the format of the data you're reading. You can specify some of the actual options depending on the format. So for example, for JSON files, we're actually specifying Spark DataFrames can infer automatically the schema, so you don't need to declare the schema anymore. But in order to infer schema is actually expensive. It requires looking at data. You can actually pass it a sampling ratio. For example, only look at 10% of the data. Tell me what the schema is for this data frame, this JSON file. And then you can call O. And same thing with like writing the data frame out to somewhere else. So it's on each of the data frames, the write method. And essentially, after the write method, you have the builder have to specify formats, how you want to actually structure the data, how you want to partition it, what kind of data format do you want. So the really the read and write just returns a filter for saving reading data and saving data. So there is actually a data source API that's defined for Spark and Spark DataFrames, and any third party can implement the data source API to provide new data format support. So there's built-in support for like JSON. You can use JDBC to connect with database. I actually got an email from somebody that they use the Spark JDBC to connect to their production MySQL database. What happened is they have a 30-node Spark program, 30-node Spark cluster, and they have a single node MySQL database. And they started launching, it basically started DDoSing MySQL. And what he did was eventually his MySQL survived, and he loaded about over 1 billion rows out of 1,700 different tables using the one of the JDBC data source from Spark. So it's actually a pretty good way to do ETL. Just getting data in from pretty much any kind of format you want. It's digging into any kind of format. So there's actually very good support for Parquet, which is a columnar data format, very popular in the Hadoop ecosystem. And you can read from Hive tables, you can read from S3 and all. And because there's a third-party data source API, the data sources are built by the third-party community. So this includes like Elasticsearch, this geospatial format called DBase, this HBase, Cassandra. You can actually go from Redshift, NetSQL, and all of that. You can find more at the Spark Packages website, which basically lists the different packages, third-party packages you can use. The other thing is kind of neat about Spark DataFrame is in Spark there's another project called MLlib, which is essentially a machine learning library. And what MLlib provides is another abstraction called pipelines. That's actually building on top of data frames. So you can use MLlib pipelines to specify a machine learning workflow. For those of you that use scikit-learn, it's actually very similar to the scikit-learn pipeline. It's actually inspired by the scikit-learn pipeline. So as an example here, I'm specifying essentially a data pipeline to tokenize some word, and hash the word into smaller buckets. So this is like the hashing is to reduce the feature space, and running logistic regression. In this pipeline, the input to the pipeline is essentially a data frame, and the output of it, it's a data frame plus a model, machine learning model. So one way to look at Spark data frame is how does it compare with a single node data frame? So single node data frames, usually people use it to process a kilobytes of data to about in the range of hundreds of megabytes. Once you go beyond that, it's becoming a little bit funky. It's kind of slow. And usually the strict memory requirements, it just takes forever. And a lot of them are also single threaded. So you can use Spark to do a very little amount of data, although it might not make a lot of sense when you have a kilobyte of data to process. But you can do that. And you can use it essentially just building on top of the Spark engine itself. You scale it to a much larger process, a much larger data size. And what I often do is actually I use Spark data frames on my laptop with 8 cores to process sometimes gigabytes of data, which ends up being much faster than you using R or Python, or 10x or R, just because those are single threaded, whereas this one you can use multi. But it's really not about Spark or R. For those of you that have seen this slide before at Big Data LA Day, I just want to stress again, it's not like a war between the two camps. As a matter of fact, we made Spark data frames and the single node data frames actually integrate very well. So you can actually freely convert between the Spark data frames and single node data frames. Now you have a very large Spark data frame, you cannot convert it to a single node data frame. The single node data frame requires you to have all data to fit in memory of the single node. But what I usually end up happening in a real data processing pipeline is to start with a lot of data, assuming you have one big data to work with. But after aggregation, after some sort of filtering, the data size shrinks to a much smaller scale. Like for example, it's only 24 hours in the world. There's only 800 or 700 people that contributed code to Spark. Running aggregation by those size is not going to have big data after that data processing. So this is actually when, for example, you might have scripts, you might know the visualization really well on R or on Python. being able to convert from a larger data frame, shrink it down to smaller ones, and then convert to a single node data frames. It's actually a very useful feature because it opens up essentially Spark to a huge visualization ecosystem, open up to single node machine learning libraries, and also like statistics libraries. So let me just show you one very quick example. So here, so this is timetable, if you remember, it's a Spark data frame we created just for 24 hours in the day. And here I'm just grouping by hours and running an account. And you can actually just call 2 pandas to convert it to a pandas data frame on a single node. And then you can just call whatever you like. And here I'm just using matplotlib and calling the plotting on pandas. So here, this is your just plotting. And you can use, in the case of RDD plots, it's a very popular choice. You could easily just convert Spark data frames in the R language to the R data dplyr, and then run ggplots on it. So in the last sort of 10 minutes or so, I'll go into a lot of the more details of how data frames actually work internally. Because it's actually fairly different from all the other data frame implementations out there. So before that, for those of you that use Spark and know what RDD is, bear with me. So Spark, the core abstraction in Spark is a thing called RDD. One RDD is a distributed collection. And it's not really, but the original Spark API, that's not the data frame API, essentially works by you pass usually defined functions to the Spark. So this usually defined function are usually in the form of closures or lambda functions. And the way it works is you have a Java or Scala API. It's basically usually give me a function. I run this function on the records. If you usually give me a Scala function, I run it in Scala, so JVM. Give me a Java function, it's also running in JVM. If you give me a Python function, I have to run it in Python. The way DataFrames works is actually slightly different. In DataFrame, we're actually, what's happening when I'm doing all those selects, group bytes, and all of that, is I'm building up an intermediate representation called logical plan. And this is actually what's basically initially developed for Spark SQL, or logical plan. So the logical plan is essentially just an intermediate representation that tells Spark what's the semantics of the computation that needs to happen. And when we need to execute it, there's actually a related optimizer called Catalyst that runs through the logical plan to generate the actual physical execution plan. And if you look at if you're going to look at the details of all the language bindings, Java, Scala, R, and Python, they all really just wrappers around this logical plan. So one benefit of this new approach is actually now it's very easy for us to build new language bindings. So in the case of, so R support was introduced in Spark 1.4, which was released last month. Essentially in about 1,000 lines of code, we added the whole Spark R support with our data frames, distributed data frames. And the whole Python data frame that was demoing using the Python language was actually initially built over the course of a weekend by actually this guy David Steele, who rebuilt all of Apache Spark in about 2,000 lines of code. Now, of course, over time they grow with better error messages and all of that. But you said that it's very simple to actually trivial to build this language front end. And now there are sort of new bindings being built for Clojure, Pascal, and all of that. Pick your favorite language. Feel free to build a front end for it. The other big benefit of this is performance. In the case of the old API, because users actually pass exposure to lambda functions, if users write in Python, you actually have to run Python. But Python is actually fairly inefficient in general compared with the JVM. As a result, the Spark Python API is actually much slower than the RDD API in Java and stuff. But in data frames, because they all get compiled really down to the same code for execution with the same intermediate representation, and you actually get the same performance just across all the languages. unless you use UDF. The other thing about performance is, so if you remember, in Spark DataFrame, there's an intermediate representation called logical plan, and there's a relational optimizer that runs through. This is actually very different from the single node data frames. In a single node data frame, usually as soon as you type some operation, like filter, you build up a new in-memory representation. Essentially, the filter itself specifies execution. It doesn't specify the meaning of execution, it specifies execution itself. It's a very subtle difference. It's actually very powerful, the way we did it with Spark. So then let's do give you one example. So let's say you have two data sets. One data set is just some event log you have for all the people that visited your website. And you have another data set that you probably obtain, let's say through a database, a data source API from MySQL, the production database. So you get a list of users and event logs. So you want to correlate. So in DataFrame, it's pretty easy. You just join the two things together. But let's say after the join, you're only interested in looking at recent events. So you apply a filter on it. This is essentially a logical plan that's being built for this data frame. So you have two data sets with two scans, and then you join the data sets together and apply a filter. Now, if you use pandas or use R, like dplyr, what would happen is, as soon as you define how to load users, it would load the user thing into memory. And as soon as you define how to load logs, it will load the logs into memory. And right after the first line, you type join. They will join the two data sets together, and then they will apply the filter. The problem in this case is this join is fairly expensive level of data. Sometimes not even a lot. But let's say if you have 10 years worth of data and you're only looking at half a year worth of it, you'd be essentially just wasting 20 times the computation power. So in the case of Spark DataFrame, because the logical plan really doesn't do the execution. It goes through an optimizer to do the execution. Spark will see this whole thing and then understand that I have a filter on top of it and I have a join. And because the join is actually an equi-join in an equi-join, it's actually safe to push the filter beneath the join. And as a result, the actual plan that would be executed is essentially I will run the scan, but I will do the filtering immediately before the join to actually reduce the cost of the join. Now, but it goes more than that. The data source, third-party data source API I told you about, actually is more naive than just dictating how to read data. It would actually pass to the data source some of the filters and predicates that the user wants. And as a result, if the data source is powerful enough, you can actually skip data in a more efficient way. So the best way to process data, the fastest way to process data is to not to look at it at all. And skip looking at it. There's no cost. Now, and this is very interesting. For example, you're loading MySQL. Let's say I'm only looking at my users for LA. I have a filter on user equal LA, or location equal LA. The MySQL JDBC data source implemented for Spark will actually push that filter into the MySQL query itself. As a result, the data we fetch from MySQL doesn't include any users outside of LA. And there's also other interesting things that can happen. For example, in the case of Parquet, it's a COM or sort of file format. And in that case, a lot of the data will actually encode in a dictionary encoding, which means strings gets turned into integers. For example, there's only so many cities in the US get represented in integers under the hood. Then it's actually a lot faster to compare integers than comparing strings. So if you use Parquet, we'll actually turn the, if you have a filter on LA, you'll probably get turned into, say, number 100 and run integer comparison. So now going back to the example, logical plan, the more optimized plan I showed you earlier. But if the data source is smart enough, for example, like MySQL or Parquet or any of this, you can actually push the filter down to the data source. So by the time we actually go read the data, we just skip all the data we don't. So for those of you that are actually curious, if you use to use a data frame, you could actually just call explain function on the data frame. This, if you're familiar with SQL, it's actually similar to SQL explain, but in a way a little bit more powerful. So you can see, for example, this is the logical plan. I have a relation, basically like a data set, and I have some filter on top of this data set, which is author name equals Reynold, and then I have a project running on top of it. And then this analyze plan is like how it's actually optimized for execution of it. In this case, things are actually very similar. All right, so just last but not least, now on top of data frames, one thing that's really good about DataFrame API is Spark now actually understands exactly the semantics of computation. Like for example, is it a filter? What field are you filtering on? What value are you comparing? So we're actually building, essentially revamping the Spark execution engine under this effort called Constant. For those of you that read my blog post, it's actually more details in the blog post. But the idea is, because we now have logical plans, which is an intermediate representation, it's very easy for us to swap out the underlying execution. For example, when it's running on a single node, we could actually have one kind of execution optimized for a single node. When it's running on a cluster, it might be a certain kind of execution optimized for a cluster. Now, Project Constant is essentially a new execution backend that focus on just improving the speed and performance of the thing. And the three major efforts of it. One is code generation. So essentially, just like generating the most optimum code for the execution plan, and then updating a lot of the algorithm to be cache efficient. So for those of you that care about like, high performance optimizations, basically nowadays in 2015, performance optimization is mostly about how do you deal with memory hierarchy and caches. And the other one is what we call binary parsing. And the idea here is because now we know the semantics of the object and all that, we can actually bypass the JVM object function and just manage the memory ourselves to make it much more efficient. Yeah, to give you just a sneak peek. Most of Constant will be ready by Spark 1.5, which will be released, I think, in September. So we're testing this new backend we're working on, and this is just on some. This is actually some data sets coming from user. We're trying out the bleeding edge master branch Spark, and on his own workload. One problem with his own workload is he didn't try to tune it. So the garbage collection actually kicked in at some point, which actually significantly slowed down the performance. So you can see there's actually not a lean, it's actually a really bad drop from 1x to 2x data size. When it has 2x data size, the time increase is almost like 6-fold. And the reason is because it was doing garbage collection. He could tune it to actually make it better, but it's kind of it's painful to do that. With the new execution mode, with the code generation of this, we actually managed to bring that time down substantially low. And you could actually just keep scaling out the data set. With data frames and with the new Constant backend, we'll talk more about Constant by the time Spark release, but not just a teaser. We think Spark will actually look fairly different. Data frames is really about making Spark even easier to use by a lot of data scientists and engineers, just by giving them the tool they're already familiar with, regardless if it's Python or Scala and Java. And Tungsten to make the Spark essentially much more efficient now with the data frame front-end enabled. And we do see everything we'll be building on top of the new data frame API in Spark in the future. This goes to, I mean, Spark SQL is essentially the same as data frames in a way. Spark Streaming is one thing that actually doesn't run on data frames yet, but there will be streaming data frames coming probably towards the second half of this year. And machine learning is already building on top of it. So that concludes my talk. Thanks. Any questions? I can take a few.
Yes. One thing that I've been struggling with is to partition my key data and then send each data frame partition, each set into a single node R process?
Either the next version or the version after that.
Okay,
It's
so
actually one
I
of the-
shouldn't try to do it with this version.
Well, it works, but it's kind of clunky to do it right. It doesn't work in R. That's the thing. You could actually do it in other languages. Right? So the question is, if I have a very big data set, correct me if I'm understanding it correctly. I think the question is, do you have a large data set? Let's say you have the population of the United States, and it doesn't fit in the memory of a single node. But each state, each city might fit in the memory of a single node. And you want to run some R model or some R statistic stuff on the individual state. Are there ways to facilitate that? Is that?
Yes.
So I've been asked that multiple times. So right now you could actually run it in Scala or Python. Because in Scala and Python, on each of the individual nodes, once you partition it, you could actually call arbitrary commands, including system commands. You can actually launch an R program on the individual node.
Is that like a schematic?
Yeah, very similar. In R, there's no API for that yet. So which is it's kind of interesting. But I think it will either come in 1.5, which is September, or 1.6, which is the end of the year. So Spark follows a 3-month release cycle.
Does that have a name yet?
Well, just the R, it will be a feature of the R data frame. And the other feature that's related is you might have a small data set that fits in the memory of a single node. But you want to run some machine learning training on it. But you usually do a lot of different parameters, or different set of parameters to do the machine learning training. As a result, running all those on a single node is kind of slow. So you want to use Spark to broadcast a small data set and parallelize the different parameter sets running in each of the thread on your server, run individual R training model. So that's like another thing that's similar. We're thinking about how to design this API and make it work. But right now I can do it. It's just the reason we haven't provided as out-of-the-box support, we're not sure what the API should look like.
Would it make sense to use Spark SQL and write out these small data sets on each partition?
You could do that. Yeah, you could definitely do that. I think there was one. Yeah, another slide I wrote was, I actually mentioned GPUs in my own blog post. I think it would make it easier to do something like this because it's another layer. They would compile certain parts of it into GPUs. It's not something we're actively experimenting with right now because I think there's only a very niche domain that GPUs are really powerful for. Like some of the deep learning stuff. Yeah. So you could already run. So by the way, Spark let you run arbitrary code on each individual node. So you could already run, for example, you could run like a thing or some other. So you could like write a GPU program with OpenCL and run Spark and use Spark to code. You can already do that. But out of box support, not yet.
The data frame methods for finding back to
Yes, absolutely. Here, I am table.write.rk. I think that just works.
So what's the question?
The question is, can you write data frame onto HDFS? Here you go. You can change the formatter. You even partition it like. Depends on what you want. Depends on what they do. Yeah. Yeah. So I think if you're doing mostly aggregation, filtering, and common statistic functions, doing it on data frames actually usually ends up being more efficient, and over time it ends up being even better over time with like constant on that. One other thing is it's actually not. it's not like a binary choice. You could actually do something like this. So you could actually call a map function on a data frame. So for example, here, I'm just running a UDF, and actually, I think this one might crash actually, because X is not a value, it's actually a row. But I think you can do something like this. Yeah. So you could actually convert, and you could also like convert RDD back to different variables.
Yeah, we'll come back to learning on how to start the example like for right one model. Can you actually partition one model and different like running a model first? Because not all of them.
Yeah, absolutely. So that one I was talking about, you can call the single node machine learning on each of the thread. But the machine learning library in Spark itself actually trains in parallel on the large data set. So that one doesn't.
Not all of them are everything.
Yeah, I mean the ones that are implemented. Yes, absolutely. You're absolutely right. There are algorithms that are inherently sequential, and we didn't implement it because we can't implement it. So, but usually, I mean, you usually don't care as much about the specific algorithm, more about the class of algorithms that might solve that specific problem. And usually you can find at least one that works. So you could just go actually. So there's actually a whole class of algorithms. I mean, all of this have basically distributed, parallel distributed algorithms. You can just look it up. Yeah.
So it shows here that DataFrame is what is access is that, but what if the optimized pattern was equivalent to the optimal pattern?
Yeah, it depends. Usually, yes. So, by the way, don't read too much into the first half and the second half comparison. I think what happened is, so I think you will see cases where DataFrame might be actually slightly slower. You see cases DataFrame will be a lot faster. After tungsten, you should only see cases where DataFrame should be like much faster. With tungsten, I think yes. Even when what you do is very similar, because tungsten actually generates a lot of the code that's a lot more efficient than what the user typically writes. Like, can you just write the same code to achieve the same performance? Absolutely, you could do it. But it's sometimes to do those is kind of annoying. For example, what the generic code would do is you avoid any allocation. So you reuse, for example, all the memory you can do, and for users to write it, kind of annoying. So you can get to the same performance if you want, but because it's, I mean, C is a lower level API. But usually the more idiomatic way of writing a lower level API won't get to the high performance that the higher level API can automatically optimize.
Just do one more question.
Why is it improved? Because it's actually no longer run in Python. All it does is there's a front end that's in Python, and the front end just tells the JVM backend that I'm running a select, and this is what I'm selecting on, for example, and this is what I'm filtering. And as a result, all the actual execution is in the JVM.
Reynold will be around for a few more questions later. Josh has a few quick announcements.
Yeah, if anybody wants to take a data center tour, you're more than welcome. Amit is going to be walking everybody through, answering a few quick questions. It's not going to be too extensive because it's such a large group. But if anybody wants to come tour the data center, you're more than welcome. We can be lining up, as soon as he's done with the discussion and answering questions. The only thing that we ask is don't bring any drinks or any food into the data center floor. We don't want to have any accidents. But once this is wrapped up, we'll meet up here at the front, and then we'll bring everyone on the tour.
Thanks, Reynold, for hosting.
Thanks.
Get the slides later, right?
I'll send you the slides later tonight.
Cool.
If I don't send it